почему бы и нет? Сейчас я... Угу. Вот это terrible. Ужас какой. Я только что обнаружил, что я взял не те записки. Я вместо своих записок взял совершенно другую стопку бумаг. Все забыл. I'm completely sorry. I forgot all my notes at home. Instead, I took wrong one. Well, I'll try to remember what I have written there, but at the beginning, I'd like to say I'm sorry for that. It's a pity. Well, our next speaker, Pavel Saponov, is still ill. He got COVID-19, and taking this opportunity, I'd like to continue my talk from my lecture from the previous time. And today I'm going to tell a short story about problems and examples of explicit commuting differential operators. And I'll give a survey of problems related to them. Well, of course, it's a pity that I forgot my notes. Certain examples I could take from my book, which is fortunately with me. Everybody who wants to get it, just ask me. I have a lot of copies of this book. And this book is about the theory of commuting differential operators in dimension 1. Well, you see it's thick enough, and it contains a lot of examples, a lot of different and difficult things. Take it. Okay, let me start. So last time I have formulated certain conjectures related to the Dixmere conjectures and related to the theory of commuting ordinary differential operators. And today I'd like to make short review together with certain still open problems since our seminar is still for students, and I hope those who want to solve certain problems can attend and try to solve something. Just a moment. Yeah, now my voice is here. And since I have formulated certain problems about commuting ordinary differential operators with polynomial coefficients, I will discuss certain points in more details. First of all, let me write down certain examples. The first, the most interesting examples are related to so-called Lamé operators. Well, what are the Lamé operators? Let us assume that we have a field of complex numbers, k is equal to C, and then for each number m from K, we consider the following operators. Lm is equal to D squared plus m plus 1 P of x, where P of x is a Weierstrass P function, and d is the derivative with respect to this variable x. I'd like to say that P is associated to some elliptic curve, and we take x to be a local parameter at 0. At 0 point on this elliptic curve. Well, then P of x in the neighborhood of this point is equal to 1 over x squared plus O of x minus 1. It's a parabolic function on our elliptic curve, and it has a pole at 0. First of all, let me recall certain examples which were known already from the beginning of 20th century. Namely, let's consider the following operators. So the question is, let me pose one question first, and I'll continue with examples. When Lm is determines a quantum completely integrable system of rank 1. That is algebraically integrable. What I mean here, so LM itself, so the one operator in dimension 1, always determines us a certain quantum completely integrable system in the sense of definition I gave before. Then last time I introduced the notion of rank, and the question should be understood as follows. We consider a centralizer of this operator in the ring of differential operators. So our operator LM belongs to D, which I just can take L. Or just let me take a ring of differential operators on our curve E this time first. And then we can take a centralizer of the differential operator in this ring. Then it is known since Isaiah sure the centralizer of any ordinary differential operator is a commutative subring in this ring. And by the general algebraic facts I told before, this centralizer determines us a quantum completely integrable system. If this system has rank 1, in the sense of the rank which I gave before, then it's called algebraically integrable. These are the most interesting quantum integrable systems. Because, as I said before, these systems admit exact solutions. We can write explicitly common functions, common eigenfunctions of these operators. We can quite explicitly write down the coefficients of these of these operators, and so on. So the general picture is the following: we take the centralizer.
This is the construction of integrable. This is the integrability construction. What you describe now. When you pass to the centralizer, this is the algebraic integrability.
Yes. Okay. Well, the algebraic integrability is the case when the rank is 1. So I consider centralizer of this operator, then it is known since sure that C of LM is commutative, and therefore it is a quiz. It is a quantum completely integrable system. By the general algebraic properties I told last time. Then the question is when LM determines quantum system of rank 1. So when this centralizer has rank 1, this is the question. And now the answer is known. I will tell it a little bit later. This is a beautiful answer because these Lamé operators are beautiful examples of Schrödinger operators with a certain potential. And moreover, amazingly, the answer is known for any potential here. So the answer when LM is algebraically integrable is known. But the first examples of these algebraically completely integrable systems were known since Wallenberg and Schur.
Sorry.
Yeah.
Schur proved that all centralizers are commutative.
Yes.
And hence it is always an integrable system.
Yes. The question, when are they of rank 1? When are they of rank 1? So,
sorry.
Yeah.
Could you please remember the definition of rank?
The definition of rank. So rank I recall that rank of B, where B is subring of differential operators. We have two possible definitions. The first one is a great common divisor of all orders of operators from B. The second definition is that it is a dimension over K of the space of common functions and phi is a point, is a generic point. Generic point of B.
So if the centralized has rank 1, then it is actually quantum integrable system, right?
Algebraically
Algebraic.
integrable quantum. So it's a QCIS, which is algebraically integrable. In the theory, these are algebraic integrable quantum complete integrable system in the sense of definition which I gave before. This was definition due to Breimer-1, Etienne-Koff, and Katsgori. But of course, such objects were studied before in Novikov's school, and Novikov called all such operators, which determine rank 1 commuting integral operators, as finite zone operators. So let me make a remark here. Another terminology. From Novikov's school. Such NM are called finite zone operators. Well, this terminology has its origin in analysis. So, well, if you consider this the spectral problem for these operators on a real line, then there will be a finite number of gaps. So historically, such operators were studied by people from integrable system, from analysis, and they studied the spectral problems of Schrödinger operators, like at our seminar, like people whom you know very well. And since that time, such operators were called finite zone operators. But in fact, this problem is purely algebraic because we just are interested in operators whose centralizers have rank 1. But the solution to this problem is very non-trivial. It includes many things, both from algebra, algebraic geometry, and analysis. And the answer actually was for this question. The answer was found by Novikov's school, and I will give this answer a little bit later. But first, let me start with first examples of such operators which were discovered by Wallenberg and Schur. Just first examples of such type. The first examples of such type. let's consider two operators. So this Wallenberg. Mm. 1903. It's very old, more than 100 years ago. Let's consider two operators. L, which is equal to d squared plus some function u, and p, which is equal to 4d cubed plus 6ud plus 3u prime. U prime means the derivative with respect to x. So u depends on x as usual.
This is not Lamé type operator.
Yes, because the Lamé operators are called when the potential has a special form. They are defined a priori on certain elliptic curve. But Wallenberg considered, well, he also considered elliptic curve, but he in fact considered a very simple case. Let's assume that we have two operators of order 2 and 3, and the question is when this operator commute. Well, when P and L are equal to 0. This is the question. He discovered a very simple.
So x is again a parameter on elliptic curve, or some parameter in on just a straight line. X here.
It's just a variable.
Just variable.
Yeah. D is equal to x. Well, we can check that direct check shows that the commutator of L and P is equal to the following expression. It is equal to 6 u prime plus u prime. This is a sort of nonlinear equation. This is a part of well-known Korteweg-de Vries equation. Let me recall that KdV equation reads as ut is equal to 6 ux plus uxxx. So it is a hint that this relation, this commutation relation, is related to a certain very well-known nonlinear partial differential equation. And then Wallenberg says that the answer on this question, this P and L commute if and only if U has the following type. Either U is equal to minus 2 P plus Weierstrass function. Well, this is a Lamé operator of x plus alpha, where alpha is a constant, or U is equal to minus 2 over cosinus, or just U is equal to yes, I'm sorry, but this blackboard is too small. Yeah, and or U is equal to minus 2 over x plus alpha squared. So these two cases are degenerations of this one. So it's well known that the P Weierstrass P function degenerates to so-called trigonometric a function autorational function if we degenerate the elliptic curve. So, this is a function on a singular curve with one nodal singularity. So this corresponds to the case when we take an elliptic curve. Elliptic curve is just a torus, and if we shrink one cycle, then we get a nodal singular curve. So this corresponds to a usual elliptic curve, and this corresponds to a cuspidal elliptic curve when we have one cuspidal singularity. Well, then this is the answer when these two operators commute. And why I told about elliptic curve? I told about elliptic curve because these two operators satisfy the following commutation relation, namely p cube is equal to 4 L cube 4p squared plus g2p plus g3. And this is exactly the equation of an elliptic curve in canonical Weierstrass form. I mean, the affine equation of an elliptic curve. When we take just the usual projectivization of this curve in CP2, then we get a usual elliptic curve. Exactly. So they commute if and only if U has one of these three types, and in that case they satisfy this equation. So they are algebraically dependent and satisfy this equation. Good. Okay. Well, you see here that we have three main cases, and this dictionary holds on also in higher dimensions. Amazingly, if you consider Schrödinger operators in many variables, they are called then Calogero-Moser operators, then it appears that corresponding quantum completely integrable systems will be algebraically integrable also if the potential has one of similar forms. So it will be as a combination of some p functions or trigonometric functions or rational functions. This is very interesting. First it was studied by Wallenberg, then by Schur, then by many others. But and in this case, of course, the rank of the ring generated by these operators is equal to 1. Then we have the rank of the ring B is equal to 1, where B is just a ring generated by these two operators, L and P. Okay. By obvious reason, because they have orders 2 and 3. The great common divisor is 1, and therefore the rank is 1. Okay. Now, the answer for Lamé operators is the following. the answer for Lamé operators look similarly. So the centralizer, the rank of centralizer of Lm is equal to 1 if and only if M is a non-negative integer number. This is a very interesting answer. It can be found in two papers from beginning of 90s by Chalach and Veselov. It is shown here, Chalach, Veselov, 90s. So there are two big papers where this history is written carefully. And more precisely, for any M, non-negative integer, there exists an operator Q of order 2m plus 1. So the order of Qm just equal 2m plus 1. Such that these two operators commute, and therefore the rank of the ring C generated by these two operators will be equal to 1, because the order of Lm is 2, the order of Q is equal to 2m plus 1, therefore the rank is equal to 1, and therefore the rank of the whole centralizer is also equal to 1, yeah, because the centralizer contains this ring, obviously. And in this case, these two operators satisfy the equation of such type, where Pm is a polynomial of degree 2m plus 1. And this is exactly the hyperelliptic curve. This is a curve which we study at a course of differential geometry when we talk about Riemann surfaces. We can obtain this surface by gluing two copies of R2, glued by cuts between the roots of this polynomial. Do you remember that? No? It's the Riemann surface of such type usually studied in the course of differential geometry, at least at Moscow State University. I believe that it is also in all other universities. Okay. In fact, we can even more or less explicitly write down the common eigenfunctions of these Lamé operators. These are so-called Hermite functions, but I will not give details here, particularly because I forgot my notes today. But nevertheless, this is a beautiful example when these type of Lamé operators are algebraically integrable. And of course, these operators appear quite naturally because these are Schrödinger operators, right? I mean, it's just Schrödinger with certain potential. And in higher dimensions, people also study such sort of operators, in particular in a series of papers by Veselov and his school. The Collagera motor operators were studied in great details, and the similar question about algebraic integrability of these operators raised in these works. Next, but okay. But since the operators with polynomial coefficients are of special interest, let me tell some words about commutative subrings with polynomial coefficients. These examples are also especially interesting. And now assume that B is a commutative subring inside the first Weil algebra. Then there is a usual obvious question. What is the rank of B? What is the rank of B? So in particular, we are interested in are there examples of rings of rank 1, 2, and so on. Let me start with the first example, and then with the first example of operators with polynomial coefficients. So Lamé was one important example, and later I will tell about analogous examples in higher dimensions. These are so-called algebraically integrable Collagera-Moser operators. And these operators have a very rich history and rich mathematics. The first example of commuting operators with polynomial coefficients was given by Dixmier, obviously in the same paper where he formulated his famous conjecture. And these are the following operators. Well, assume that Q, put Q to be equal to d squared plus x cubed plus lambda. And lambda is some complex number. And then consider L, which is equal to Q squared plus 2x. And then take P, which is equal to 2q cubed plus 3 qx plus xq. Now, these are again two operators of orders 2 and 3. This is the most studied case. So the people from the beginning of 20th century try to classify all operators of order 2 and 3 that commute. And then it showed that L and P commute. And moreover, they satisfy the same Weierstrass equation. But in this case, this Weierstrass equation has a very simple form, just this one. So there are no other terms here. Very simple, very beautiful equation. So now again for lambda is not equal to 0, we obtain an elliptic curve. So this is a smooth curve, which is topologically just a torus. And if lambda is equal to 0, then this is a
we can do it for all this, for all lambdas.
yes, for all lambdas. So this is a series of examples depending on this constant lambda. Well, this is the first example of Tixmere. And at this point, I need to explain a certain history, history about this example and further considerations. So this was the first example with polynomial coefficients. But I need to say that, that in this case, he also showed that besides the rank of the commutative subring generated by these two operators, L and P, is equal to 2. This is also a statement due to Dixmere. Now, before we started commutative subring of rank 1, these are so-called algebraically completely integrable systems, and this is not algebraically integrable system because it has rank 2. Well, as I told last time, there is a very good classification theorem of commuting ordinary differential operators in rank 1. For these rings, we know almost everything. There are explicit formula due to Krichyver in terms of theta functions of Jacobians of algebraic curves. And even if the curve is singular, also a lot of norm in this case. But for commutative subrings of rank greater than 1, fewer information is known, fewer results. So namely, I'd like to say that practically all commuting rings of differential operators with polynomial coefficients has rank greater than 1. And I will explain this in 5 minutes. I'll state this result quite explicitly. But some history related to this example. In 80s, Novikov and Krichyver constructed a series of examples. Well, practically they got almost all operators of such type. Series of examples of commuting operators L and P where the order of L is equal to 4 and the order of P is equal to 6, which satisfy I should put here L. it satisfies the same equation. Well, not the same, but a general equation of elliptic curve. So more precisely, they constructed almost all such commuting operators under the condition that this equation determines a smooth curve. So more precisely. We constructed almost all such operators. With, well, let me denote the curve which is determined by this equation by C. In the case when this curve is smooth, then they gave the almost complete list of such operators. In their examples, and it is important in the whole business with these commuting operators, they assume that both operators are monic. I mean that the highest coefficient is 1. It is important because the whole theory, which classifies such commuting subrings of ordinary differential operators, works with monic operators. The problem of classifying any commuting operators is reduced to this one by certain change of variables, by conjugating with certain function, so that we can reduce the problem to the problem of monic operators. But in fact, this reduction is not clear until the end. There are some problems, and I will tell about them now. But then they reported this list of examples at the Gelfand seminar, and Gelfand asked how the example of Dixmier, series of examples of Dixmier, are related to these examples of Krichever and Novikov. And the answer on this question was found by Grinevich, because the list of Krichever and Novikov looked very complicated. So they constructed quite explicit list of examples with coefficients given in terms of these Weierstrass P functions. And the formula are huge. So if I will write this formula, this will take the whole blackboard here. And it was not clear at all how this example of Dixmier fit into this list of Krichever and Novikov. So Grinevich found a condition when the lists of Novikov and Krichever produce an example of operators with rational coefficients, and in particular with polynomial coefficients by Dixmier. But then Gelfand asked, well, okay, we know just one example of a pair of commuting operators with polynomial coefficients for which we know the spectral curve. So this equation, this algebraic equation which determines a curve, is called a spectral curve in this theory. And the question by Gelfand was, could we produce examples of polynomial commuting operators with arbitrary spectral curve and with arbitrary rank of the corresponding ring of differential operators. A question. Are there examples of operators L and P which commute such that the rank is arbitrary and the curve, which is determined by some polynomial relation f to 0, has arbitrary genus.
All examples like which we are knowing of genus 1.
Exactly. They are considered only operators of order 4 and 6, which has an elliptic spectral curve. Which has elliptic spectral curve. Gelfand posed this question, and the answer on this question is appears to be positive, but it was discovered only after 2000 in series of works by Andrei Mironov and Mokhov. So Andrei Mironov first discovered a series of beautiful examples of commuting operators with polynomial coefficients, which was then developed by Mokhov to give the question, to give the positive answer on this question. Yes, Mironov. Mokhov. So,
Everything is arbitrary.
yes.
No relation.
No relation. Well, just a series of examples. These examples are very sophisticated. In fact, the first examples by Andrei Mironov, who was just a discovery. He found and he worked a lot of time to find such examples, and then occasionally he found first examples of such type, and then they were developed later to produce all possible examples of operators with arbitrary rank and genus with a spectral curve. Well, of course, in a sense, this picture is not complete yet because these are just examples. Of course, the curves, the spectral curves were not arbitrary, but they were all hyperelliptic. And the polynomials have the form, the L is the polynomial of order 4, and P is the polynomial of order 4G plus 2, where G is the genus of the curve. But nevertheless, they are interesting. They are first examples with polynomial coefficients with such property. Before their works, there were no explicit examples of commuting polynomial operators of higher rank and genus at all. And remarkably, this story with operators 4 and 6 is not completed yet, even in this simple case, in the following sense. So this is the history is very rich here. The history about this, operators from 4 and 6. Just let us mention several other works. Frederica Grünbaum, then after the works of Krishev and Novikov. This is my battery. Yes, unfortunately.
I have battery.
Really? Ah, that is beautiful. Do you have iPhone?
Yes.
Ah, beautiful. Oh, thank you very much. Oh, thank you so much. Oh. Okay. Then Frederica Grünbaum, in the same late 80s, calculated the whole list of commuting operators for the 4 and 6. Again, L is monic, of course, because as I told before, the generic case can be reduced to this one by conjugating with some function. But it's calculated with the help of supercomputer. Supercomputer of 80s. It was an amazing result. Well, of course, it's possible. Well, it's a difficult task even for such simple cases when the order are 4 and 6. People needed a supercomputer to calculate the whole list. Of course, this list contained the list of Khrushchev and Novikov for sure, but his work is complete. And in particular, it was very unusual to find certain examples of operators of order 4 and 6, for which the ring generated by these two operators has rank 1. So if we just look at this ring C of A and P, a typical mistake if you think that the rank of this ring is equal to the great common divisor of orders of N and P. This is wrong in general, because this ring can be a little bit larger than it seems. And in particular, as Grunbaum found in his explicit calculations, there are operators of order 4 and 6 which generate a ring of rank 1.
In the centralizer of L, there can be operators of...
No, just in this ring generated by these two operators.
There can be operators whose rank
Yes.
does not divide, is not even. Yeah.
Yes, yes. It is quite unusual, but it can happen. It was exactly found in his work by supercomputer. Of course, in the work of Khrushchev and Novikov, all these rings were of rank 2. They looked only for rank 2 operators. And in fact, they couldn't get anything more just because they are restricted to the smooth spectral curves. It's quite difficult to find something non-trivial. I mean, certain operators which generate a ring of rank 1, not rank 2. Well, and after that, there were other two works which studied this list, this complete list of Khrushchev, Novikov, and Grunbaum, and studied the algebraic geometric data corresponding to this to these examples. This work was by Privat and George Wilson. They studied algebraic geometric datum. Corresponding to the operators from Grunbaum's list. In the case when the spectral curve is smooth, that is, in this case, it's an elliptic curve. So in all these cases, the curve, the spectral curve of these two operators is either elliptic or a degeneration of an elliptic curve. So if it's smooth, then it's elliptic curve. If it's not smooth, then it has a singular point, and then it's either nodal or cuspidal curve, like in the example before. And then only in 2016 we finished the study. It was the same study by Privilato and Wilson in the case when C is singular. So, in fact, it appears that the explicit description of spectral sheaf corresponding to these examples from this list is a rather non-trivial task. Our paper was big enough because this dictionary appears to be very difficult. Even in the simplest case of conventional operators of rank 2, to see explicitly which data corresponds to this ring and vice versa is a very non-trivial task. Okay, and
for the list of Grunbaum's.
Yes, for the list of we took this whole Grunbaum's list just because it has a compact form. It's in a sense more convenient to work with him because Grunbaum's list operates with arbitrary formal series in coefficients of operators, not with Weierstrass P functions. So we just could erase all assumptions about smoothness of the curve, and in such a way we could easily understand which spectral bundle corresponds to concrete example from Grunbaum's list. But then next question, so this was a conjecture, another conjecture, or more precisely this was a folklore result which is the following. If B is a commutative subring in the first field algebra, then its rank must be greater than 1. Well, why people believed in this conjecture? Just because there is a classification theorem which says that each such ring corresponds one-to-one corresponds to certain algebraic geometric data, which consists of a curve and of a bundle in this curve. And then there are explicit Kirchhoff formula, and as Kirchhoff told me, and other people also who were involved in this activity, so that, well, of course, this explicit formula in theta functions cannot degenerate to polynomials. But apparently no rigorous proof of this conjecture was not known until this year, when Makar Limanov gave an explicit proof, explicit explanation of this phenomena. Actually, this work appears after my question to him in 2013.
Sir,
yeah.
If you just take the subalgebra generated by by difference of the
Yeah, of course.
BDS.
Yes, of course.
Isn't
And yeah, of course. We put here a non-trivial. Non-trivial in the sense that it's not with constant coefficients, not generated by the trivial. But let me explain the answer. The answer and certain results concerning this case. There are the following facts. So the fact 1, proposition 1, says the following. So if P is a monic differential operator, here in A1, then any Q which commutes with P, let me formulate it in another fashion. So A1 belongs to a bigger ring D with arbitrary series as coefficients.
What's the difference between A1 and
If
D?
what?
What's the difference between A1 and D?
A1 is a first wheel algebra, so the coefficients are polynomials.
These are not D and C. I thought it was C times KC times.
C of x.
No.
What?
Those are. I thought those are brackets, aren't they?
Double brackets.
Yeah,
These are series.
But they look like C and D. You see?
No.
Now there is no problem.
Okay.
And before that I was sure.
Well, first of all, there is a following result. This is a certain purity of operators with polynomial coefficients inside all differential operators. It is known that if Q commutes with P, Q from D, then Q must belong to the first main algebra 2. So that means it's a centralizer of a monic operator with polynomial coefficients. The centralizer inside the ring D must be in the first wheel algebra. So in particular, the centralizer of D of P belongs to A1. If P is not monic, then it is not true. This is not true. There is another modification of Wallenberg's example. It shows that, that it is not true if P is not monic. So the property of P being monic is important. So it
Monic means that
this
the
highest
leading term is 1.
exactly, and this is important. So when we classify all commuting pairs of ordinary differential operators, as I told before, we reduce the problem for classification to a classification problem of monic operators. But how we do it? We conjugate our operator with certain function or do some change of variables to kill this highest coefficient to make it equal to 1. But if you want to understand something about commuting differential operators with polynomial coefficients, we cannot do this procedure. If we make a complicated change of variables, then we destroy the polynomiality of coefficients of our operators. And therefore, to study operators in the first wheel algebra, we cannot just make arbitrary change of variables. We are restricted, and therefore for this case, the whole classification, the whole machinery cannot be applied so easily. So we must be careful. In particular, this remark shows that for general case, there are certain difficulties. Well, but then Makar Limanov shows the following. This is just the paper of this year, the beginning of this year. He showed that if P, he showed the following result. If P is a commutative subring in the first Weyl algebra, and the rank, it's a beautiful paper, then B can be embedded into the algebra of polynomials in one variable. So in particular, the spectral curve of any such ring is rational. Singular and rational spectral curve. Is rational. So if the ring is trivial, then of course this curve is smooth, which is just a P1, the straight line. But if it's not trivial, then it is a singular rational curve. And another partial case of his result tells us that if we consider commutative subrings which contains monic polynomials, if B contains a monic polynomial, monic operator, then the rank of B is just then B is just isomorphic to C of K of T.
What is Z here? What is
Z is some formal variable, so we can.
it is not X.
It's not X. It's not X. It's just the result stating that B can be embedded as a subring of a polynomial ring. But any subring of a polynomial ring determines a rational curve. If B contains a monic operator, then B is isomorphic to the ring of polynomials. Actually, then B is just generated by this monic polynomial. Then this example is trivial. So B is just equal to K of P, where P is a monic polynomial. More precisely, not B itself, but centralizer of B. The whole maximal commutative subring containing such an operator. But in fact, it follows that for so-called elliptic rings, namely for those rings which contain a monic operator, the picture is very simple. The maximal such ring is always generated by one monic polynomial, and therefore it has almost always rank is greater than 1. So either it is trivial, it's generated by an operator of order 1, or it has rank greater than 1. Yeah? In particular, if the order of P is greater than 1, which is the usual case, then the rank of B, the rank of centralizer of B is greater than 1. So in a sense, this conjecture is true, but when we understand it correctly. In the same paper, he tried to classify all commuting differential operators of order 2 and 3, like Wallenberg, like Birch-Challenger, like Schur. And he got a result which reduced the problem of this classification to classification of certain pairs of polynomials. Well, in a sense, this is a classification, but it's not clear completely how to classify these pairs of polynomials. So we reduce one problem to another. And but this is a nice work. Finally, I have a rigorous proof of this conjecture, and we know that in fact there are commuting polynomial differential operators of rank 1, but all such examples produce singular spectral curves. Okay.
I understand why it follows from the fact that CB is equal to K of Z, then that CB is actually equal to K of P.
It is a partial case of his theorem.
So what is his theorem?
His theorem says that if B is a commutative subring in the first Weyl algebra
And has rank 1.
and has rank 1, then B can be embedded into a polynomial ring. And if B contains a monic operator,
Then it is automatically rank 1. No? So what is the
no, not automatic.
assumption?
No, not what. These are assumptions. These are assumptions.
So B has rank 1.
Yes.
And suppose B has monic operator inside. Then B actually is inside A1,
Yes.
but it's already assumed there.
Yeah.
So what's the matter then? So you have this assumption.
Yes.
This
Then B can be, can be embedded into the ring of polynomials, right?
Some formal variable, new formal variable.
Yes. Now, if B contains monic operator,
Yeah.
then centralizer must be isomorphic to K of Z. And
Right.
now, this is a partial case of
Okay.
his theorem, this is a statement. Now I should put here a line, and we can derive from his theorem immediately the following conclusion, that if you have a certain ring of commutation operators in the first Weyl algebra, and if you assume that B contains a monic operator of order greater than 1, then the rank of the centralizer must be greater than 1.
Why?
Because we know that from his theorem we know that the centralizer of rank 1 operators should coincide
There's
with
no
his
rank 1
polynomial
here.
ring.
I don't see rank 1. Oh, rank B is equal to 1.
And B is equal to 1.
Okay, rank B and rank P is the same.
If C of B is equal to the polynomial ring generated by just one operator, then the rank of this ring is obviously the order of P, right?
Mm-hmm.
Because it's generated just by one polynomial.
Yeah.
And therefore, it cannot be. So, if B contains a monic operators of a monic operator of order greater than 1, it cannot have rank 1 just by this theorem. Because from this theorem we know that if it have rank 1, then it is isomorphic to K of P. And since the rank of K of P is equal to the order of P must be equal to 1. This is a conclusion of this statement. So this is a corollary from this theorem this is a theorem of Makar-Limanov.
So it means that
This.
it means y it means B is equal to K of P. So if B is equal to K of P, then the Makar-Limanov we see that
No, now consider any ring of commuting polynomial operators, and assume that this ring contains a monic operator. Then of order greater than 1. Then the rank of its centralizer must be greater than 1. Why? Because if it would be equal to 1, then by theorem of Makar-Limanov, it should be isomorphic to this polynomial ring, K of P. And then it should be generated by an operator of order 1. This is a claim. Yeah. So if B is non-trivial, then and contains a monic operator, then its rank should be greater than 1. This is a claim. That was exactly the statement of the conjecture. So people thought always about non-trivial examples of commutation operators, right? What means non-trivial? That means that this ring are not generated just by one monic operator. This means that there should be at least 2 operators with non-trivial commutation relation. And in fact, due to this theorem, this is true in a sense. In a sense, if we consider only commutative subrings containing monic operators, and in a sense that we consider non-trivial subrings, that means that the rings not generated by operators of order 1. In this sense. It's clear now?
It's a little bit tricky. I feel that there is some kind of cheating there.
No, there's no cheating here. There's no cheating at all. So this is a statement. This is a rigorous statement,
Yeah,
and this is a corollary.
Yeah, there's still many things that I don't understand. So you assume that suppose B has rank 1, then it cannot contain monic operator of rank greater than 1, right?
No, it can contain, but then it is a degree of the generator of order 1. But if B, if B contains one, well, let me erase. Let me explain it more carefully. So corollary. So now, if B is a commutative subring, and P belongs to B as a monic operator, and the order of P is a minimal greater than 1. It's a minimal non-zero order. Of all operators in B. Then, so that means that B is not generated by operator of order 1. Yeah? Then the rank of B should be strictly greater than 1. This is a strict statement of this corollary. Okay?
I don't see how it follows from Makar-Limanov, because Makar-Limanov has assumption that rank B has 1.
Assume the converse. Assume that the rank of B is equal to 1.
Yeah.
Then we are in situation of Makar-Limanov theorem, of this partial case. By this partial case of this theorem, it follows that the centralizer, I forgot to say that it's maximal. Right?
It's equal to itself.
Maximal.
Centralizer is equal to itself.
Yes. Then by this case of Makar-Limanov theorem, we must have that K should be generated by an operator of order 1. A contradiction. And that is all.
I don't see this contradiction again. So we have by Makar-Limanov, so rank B is equal to
B is
1.
maximal and P.
Its centralizer is equal to itself.
and B doesn't contain any operator for the 1.
Okay.
But by Makar-Limanov's theorem, it must contain an operator for the 1.
Where does it say this?
Because C of B is equal to K of P,
Yeah, but here.
rank of K of P is equal to the order, and the rank is equal to 1.
Oh,
Then the order must be equal to 1.
I see. It's really tricky. A little bit.
Mm.
Yeah,
Mm.
I see.
Mm. Okay. And this is a purely algebraic result. Purely algebraic result proved with the help of Newton's polygons. So in a sense, the ideas used, they are not taken much from the paper of Dixmier.
So we're actually running out of time. It's already
Yeah.
past
Right.
7, so.
Right.
it's time to stop
Ah,
here.
wait. I see there are some
Questions?
messages chat. Or maybe. That's not messages, just. That's okay. Okay.
We're running out of.
Yes.
sentences.
Yes.
People cannot wait in here.
Yes.
So next time we shall go on. I think only we remaining. Yeah, besides me. All other people who just late. So
Yes. Well,
I think we can speak Russian now.
да. Ну, в любом случае, следующая вещь, так сказать, я закончил этот обзор с полиномиальными операторами. Здесь много еще есть вопросов, как раз вот для студентов. Много задач осталось, которые связаны там, вот с этой гипотезой Береста, с гипотезой Дixmier. Там много каких-то деталей, которые здесь до конца не ясны. Вот. Ну и судя по тому, что здесь вот работы совсем свежие появляются, все это еще актуально. А дальше я хотел рассказать про примеры вот высших размерностей, как раз про коллажера Мозера, который возникает в серии работ Веселова и Чалых.
So we shall continue next time, I think.
Yeah.
Okay.
So if I'll continue next time, if Pavel will be
No, he
still.
will not be still here.
Okay.
That's a problem. He has to pass the medical examination.
Okay.
Next Tuesday.
Okay.
The crucial medical examination, which will show that he does not have
Okay.
this infection anymore.
Okay. Then next time I can explain about these examples of Collier-Moser operators and about algebraic integrability in higher dimensions.
Okay.
Yeah, but this is a rich theory. There are many questions, many open problems, etc.
Okay, let's stop here.
Okay, let's stop here.
I think
Thank
there are
you.
no questions.
Yeah,
because
yeah.
Nobody.
Yes. I don't know when
Maybe you have.
when people left.
Actually, couldn't manage. Couldn't bear it anymore.
Okay.
Sorry. Bye. Okay. Ну что?
Так.
Ничего, двигаемся потихонечку.
Ну
На
да.
самом деле был, конечно, вопрос, какая связь между этим и
Спасибо.
тем, что рассказывал я. Но
Значит-
связь, она переход от более геометрической, более алгебраической конструкции. Это, конечно, должна была быть через... Я хотел бы в помощи квантовой группы отчасти это рассказывать.
Ну, как сказать, квантовые группы в определенном смысле слова. Сейчас нам, наверное, можно закончить это. Как там это закончить? Может,
Нужно пойти молодому человеку вот через провизор, и он тогда там выключит трансляцию.
Мгм.
На самом деле я отключил камеру от Zoom, а камеру от YouTube это было отключено вначале.
Ну да. Просто я не знаю, как это выключить. Видишь ли, тут просто в размерности 1 здесь эта теория очень сильно разработана. Я совсем не вдавался в детали там, алгебраической классификации. Вот целая книжка посвящена этому. Там очень много всего сделано. И в высших размерностях тоже. То есть эти квантовые интегрируемые системы, там много явных примеров. Они строились все с помощью разных методик. Там и теория представлений какая-то сложная, какая-то геометрия нетривиальная есть. весьма. Ну, там тоже много вопросов. Все это в каком-то смысле связано с тем, что ты рассказывал, ну, потому что эти коммутирующие операторы, они возникают там в контексте
Ну да.
квантования Пуассона, и квантовые группы тоже в некотором смысле.
Да,
даже. Ну, вот.
нужно эти, конечно, аппараты.
Но разные совершенно методы, конечно. То есть здесь чисто больше алгебраические методы, там алгебро-геометрические методы.
Деформация сюда просто неприменима.
В том-то и дело. Ну, как тебе сказать? Ну, да, пожалуй. В размерности 1, да. В размерности 2 там ситуация интереснее, потому что как раз квантовые коллажиры Мозер операторы, их можно как раз рассматривать как квантование классических коллажиров Мозер систем. Вот там как раз есть о чем поговорить, по крайней мере. Если вот, там, так сказать, немножко другая деятельность. Естественно. Ну, конечно. Ну, в любом случае, можно еще студентов послушать, аспирантов.
Ну вот, кстати, я посмотрел, могу тот самый Иван, который довольно интересно раскрутил. Так он, правда, интересный.
Зиран?
Ну, да, Зиран. Он какую-то статью, которую писал тогда, Фука и с кем-то. Они там такое разрабатывают науку, что назвать вообще не объяснить. Структуру, правда, если сюда в это дело впихнуть, я не понимаю пока. Она интересная, но она вот немножко в сторону. Вот, это можно будет послушать.